Okay, this section is going to take what we've seen about orthogonality and look at orthogonal projections. So suppose that we have a subspace of Rn. If you have any vector in Rn, the idea here is that you can break it down into two components, Z1 and Z2, where Z1 is in W and Z2 is orthogonal to W. So we've kind of seen this idea in the last lecture, but there we just gave the examples in terms of being orthogonal to a line. This works for wider things as well, for subspaces. Here is a drawing of it in 3 dimensions. So Y is a 3-dimensional vector. W is our subspace, which is a two-dimensional subspace of R3. So Y hat is the projection onto W of Y. That's our Z1. And our Z2 is the part that's sticking up totally perpendicular or orthogonal to W. Now in 3 dimensions, we normally portray it as, you have a plane and a line that's perpendicular to that. This works for multiple dimensions, so for as many dimensions as you have, the idea holds. Which leads to Theorem 8, your orthogonal decomposition theorem. It says that any vector in Rn, where you have a subspace of Rn, it can be written uniquely as your projection plus some other vector that is orthogonal to everything in your subspace. So your projection is in W, is in your subspace, and the Z is orthogonal to your subspace. And moreover, this theorem actually says that if you have a basis for your subspace, an orthogonal basis, you can actually write out what your projection is. And again, this is a formula using the inner product or the dot product that we've seen for the last couple of lectures. Theorem 9 is called in the book the best approximation theorem. So this uses the same idea. So you have a subspace of Rn, you have the orthogonal projection onto W. What that vector gives you is a point which is the closest point in W to Y. So you take any other point in W, it's going to be farther away. So this orthogonal projection, you can kind of see it in 3 dimensions, but if you have multiple dimensions and a subspace of your Rn, however big Rn is, that Y hat is the closest point that you can get to your Y and still be in your subspace. This has all kinds of applications. When you start looking at things in physics, in statistics, in other areas of the sciences, this idea of finding the closest point that to the point you're interested in, this is an important concept, and what you are seeing here is how to find that. Theorem 10 goes one step further. Here, instead of an orthogonal basis, we have an orthonormal basis, and with an orthonormal basis, you have an even easier formula for finding your projection. But again, see, it's involving that dot product. So that dot product keeps coming up over and over again. Moreover, when you have that orthonormal basis, if you take that basis and create a matrix out of those basis vectors, then you can get your projection just by some matrix vector multiplication. So your basis vector or your basis matrix times the transpose of that matrix times your vector gives you the projection, which gives you the closest point possible in that subspace. So this is a very nice result and a very useful result. So as an example, we've already we have an example of a two-dimensional subspace in R3. So if you look at U1 and U2, that's an orthonormal basis. The length of each of those vectors is 1, and they are orthogonal to each other. So now find the orthogonal projection of this vector. And what is that? Well, you create the vector U, or the matrix U, which is just the columns of U are the basis vectors. Because it's an orthonormal basis, you can use U times U transpose. When you take U times U transpose, you get this vector on the right, or this matrix on the right-hand side. So if you want to now get your projection, it's just that matrix times the vector gives you the closest point possible to your y. So that's the idea of orthogonal projections. As I said, this concept of being able to find the closest point to a vector in a subspace of Rn has applications to quite a few places in the sciences, especially if you're looking in physics or in statistics.